Okay, so here we go in solving equations that are logarithmic and exponential. All right, so first of all, we're going to just remind ourselves how to change an exponent equation to a logarithm. So if I have some base to some exponent equals a number, the corresponding logarithmic sentence would be log of this base, which is b, of that number, which is n, equals my exponent. And just a quick check, b to the x power equals n. Okay, so we're going to be going back and forth here. So in this first part, when we solve equations that have logs in them, we have this property. So if I have log base a of some number equals log base a of another number, then these numbers, if I have the same base, these numbers have to be equal. So the number that we're taking the log of have to be equal if they're the same base. And an important thing that they tell us is that m and n and a are all positive. That means that they're greater than 0. And a cannot equal 1. Okay, so we don't have a base of 1. All right, so what does this mean? It means if we have a single log on both sides, and the same base, then we can say that m and n are equal. Okay, so it has to be a single logarithm on both sides with the same base. All right, so here we have in example 1, we have a single log on both sides, and we're going to incorporate our properties that we learned the other day. So I could write this, I can move this 2 as an exponent of x. So I can say that this is log base 5 of x squared equals log base 5 of 9. So in this case, I have a log base 5 on both sides. So in that case, m has to equal n, or x squared has to equal 9. All right, so we know we do square roots of both sides, and x has to equal 3, and x has to equal negative 3. Now, these are my solutions algebraically. However, if I go back and I look up here, it says m and n are positive. Okay, so these values for x squared have to be positive. My x values have to be positive. So I cannot have a negative solution. So I'm going to cross this off. And actually, this is called an extraneous solution. Okay, and that's because this value has to be greater than 0. Okay, it works algebraically here, but in terms of our domain means that x has to be greater than 0. Excuse me. All right, so an extraneous solution is just something that we get that algebraically works but is not part of the domain. Okay, not part of the domain. All right, so in this next one, again, we're going to incorporate those properties. So here I have log base 5 of x plus 6, and log base 5 of x plus 2, and that equals 1. All right, so I can first I'm going to look at what my domain is. Okay, so I'm going to look at these values here, and I know in my domain all of this has to be greater than 0. So x plus 6 has to be greater than 0, and x plus 2 also has to be greater than 0. Okay, so this, if I think about this, this is a compound inequality, and I'm looking for the overlap. Okay, so if we think about number lines here, here has to be x is greater than -6, and here x has to be greater than -2. Okay, so my x value has to satisfy both of these sentences. So let's just pretend that I get a value of -4. And I know that -4 is greater than -2, so that would work in this sentence, but not in this sentence. Okay, so -4 would work here. In terms, if I put it in here, -4 plus 6 is +2, so that's true. But -4 plus 2 is -2, so this is not true. So in my domain, both of these have to be true. So in this case, my domain is the numbers that are greater than -2. Okay, those are the numbers that will make this a true sentence. And we'll talk about that domain in another one, and hopefully it will make sense. But here I have log base 5 in both of these, and because I'm adding these two logs together, I can use my property to write a single log of log base 5, and I'm going to multiply, because of the addition sign here, I'm going to multiply these two parts together. So x plus 6 and x plus 2, and that has to equal 1. Now, if I were to solve this equation by writing the exponential sentence, I have 5 to the first power equals x plus 6 times x plus 2. Okay. So if I solve this, this is a quadratic equation. This becomes x squared plus 2x plus 6x is 8x plus 12 equals 5. And if I subtract 5 on both sides, I get 0 equals x squared plus 8x plus 7. And this is factorable. I can factor this into x plus 7 and x plus 1 equals 0. And my solutions would be x plus 7 equals 0, x plus 1 equals 0. So x is -7 and x is -1. And if I go back and look at my domain, my x values have to be greater than -2. All right, so this one works because -1 is greater than -2, but -7 is not greater than -2, so this is an extraneous solution. Okay, so I think I call it the extra solution. It works algebraically, but it doesn't work in terms of our domain. All right, in this next problem, in example 3, we have natural logs, and if I look at these numbers inside here. In terms of my domain, I have to have x is greater than 0, x minus 4 is greater than 0, and these are ands. And I have to have x plus 6 is greater than 0. So x has to be greater than 0. Here, x has to be greater than 4. And here, x has to be greater than negative 6. All right, so technically what I'm doing is I'm looking for the number that's the largest, because that would include all 3 of these pieces. All right, so if I were to put these on a number line, and I'm just going to do that over here. So here's negative 6, here is 0, and here is 4. Negative 6, the numbers greater than negative 6 are this way. The numbers greater than 0 are this way, and the number greater than 4 is this way. And the only numbers that overlap are the numbers that are greater than 4. So my domain here is x has to be greater than 4. Okay, so that's my domain. All right, so let's look at our properties now. Here again, I'm adding these together. So I have the natural log, which means I have the same base, which is e. So I have ln of x times x minus 4 equals ln of x plus 6. So in this case, because I have the same base, which is e, this is the case of a single log on both sides. I have the log of the same base, so this has to equal this. All right, so I'm going to write that x times x minus 4 has to equal x plus 6. And this is going to turn into a quadratic equation as well. So this is x squared minus 4x equals x plus 6. I'm going to subtract x and subtract 6 to get 0 on this side. So I have x squared minus 4x minus an x is minus 5x, and then minus 6 equals 0. And here I can factor. So the numbers that multiply to be 6 and add to be negative 5 would be negative 6 and positive 1. So my solutions are x is 6 and x is negative 1. Now when I go back and look at my domain accepts numbers that are greater than 4. So 6 will work. So this is a solution. But negative 1 is not greater than 4, so this is extraneous. Okay. On the next side, we are working with some more exponential equations. And here, we are going to write this first example as a log sentence. Okay, so remember writing a sentence that is exponential in terms of a log. So this would be log base 2 of 5 equals x. Okay, so log base 2 of 5 equals x. So if I'm using a calculator, I would have to use the change of base formula, or I could use the fancy calculator that has the log of any base of a number. But remember, this is x equals, and then I would have log of 5 over log of 2. And this would be my solution set. And if I did the calculations for that and I got this is actually the exact number, but an approximate value would be 2.322. Okay, and that's when I calculate log 5 divided by log 2. All right, so this is one way to do this, is to write this as the exponential sentence as a log sentence. Another way to do this is to isolate the base and the exponent. So that means I have to divide by 8. So now I have 3 to the x power equals 5 divided by 8. And the property of algebra, what you do to one side, you have to do to the other. To get the x out of the exponent, I'm going to log both sides. I'm going to do the log of both sides. And what happens now is I can take this exponent and move it in front of the log of 3. So I have x log 3 equals log of 5/8. And to find x, I'm going to divide both sides by log 3. And x would equal log 5/8 over log 3. Now, this is the same thing as doing the change of base formula, writing it as a logarithm and then doing the change of base, because if I wrote this as a logarithm, I would still have 3 to the x equals 5/8 as my exponential. And then if I wrote this as a log, I would have log base 3 of 5/8 equals x. And to find the value of this, I would have to do log of 5/8 divided by log of the base, which is log 3. And this is the same thing. Okay, so we can write it as a logarithm and then do the change of base, or after we have the base and the exponent by itself, I can just do the log of both sides by using the property of equality, and I'll end up with the same thing. Okay, so again, this is my solution set. This is the exact value. And the approximate value, the estimated value is, I know I did this, negative 0.428. All right, so in example 5, we're going to use what I indicated up here. Because I have my variable in the exponent, to get the variable out of the exponent, I'm going to log both sides and then move my exponent to the beginning, or I'm going to move it so I can multiply it by the log of 5. So I'm going to do log 5 x minus 2 equals log 3 of 3x plus 2. So now I'm going to take this exponent and multiply it to the beginning. So I have x minus 2 times log 5, and that equals 3x plus 2 times log 3. All right, so now what I'm going to do is I'm going to distribute. Okay, so I'm going to distribute basically log 5 times x and log 5 times negative 2. So I have x log 5, and now negative 2 log 5. And I'm going to distribute on this side as well. So I'll have 3x log 3 and then plus 2 log 3. Now my goal is to solve for x. So I need to get the terms with the x's on one side and then the terms with the non-x terms on the other side. So basically I'm going to keep this here. I'm going to subtract this over to this side and then add this to the other side. Okay, so I'm just going to kind of do some shuffling here. So I start with x log 5, and then I want to subtract the part that has the x in it, so minus 3x log 3. And that's going to equal, so now I'm going to add this 2 log 5 over to the other side, and then plus 2 log 3. All right, so again, I want to solve for x. So I have an x in each of these parts, so I'll factor an x. So when I factor out an x, I'm going to multiply that by log 5 minus 3 log 3. So this now equals this whole side. I'm going to write this here. So now to solve for x, I'm going to divide by all of this. So I'm going to keep 2 log 5 plus 2 log 3. So x equals, okay, so I'm here, 2 log 5 plus 2 log 3. And I'm going to divide that by what we factored the x out of, log 5 minus 3 log 3. Okay, so now if I do those calculations, and by the way, this is my exact value, and I can do an approximation by plugging this into Desmos or a calculator. Make sure that all of this is on the numerator, and then you're dividing by all of this. And when you do that calculation, you will have x is approximately equal to negative 3.212. Okay, a lot of steps on that one. All right, so example 6 is very similar. Okay, so I have exponents in I have my variable in the exponent, so I need to get the variable out by taking the log of both sides. Now I noticed in your textbook that they use the natural log, and up here, if I would have done natural log on both sides, that would have worked as well, and I would have ended up with the same value over here. Okay, I would have just had 2 ln of 5 plus 2 ln of 3 divided by ln 5 minus 3 ln 3. All right, so let's do the natural log on this one just to kind of show that we can do both. So here I can take the natural log of both. So that's ln 2 to the x plus 1 power equals ln of 5 to the 1 minus 2x power. And because I did this ln, I can actually use my properties to move the exponents out in front and multiply. So I have x plus 1 times ln of 2 equals 1 minus 2x times ln of 5. Now I'm going to distribute like I did up here. I'm going to make this into two terms. So I have x ln2 plus 1 ln2. And then over here I have 1 ln of 5 minus 2x ln of 5. So now I have some terms that have x and some terms that do not. So I need to get all the x terms on one side and the non-x terms on the other. So I'm going to keep this term, I'll subtract that term, and I'm going to add this term to the other side. So I'm going to have x ln2 minus 2x ln 5. So I moved this part over to the left side, and I'm going to keep this 1 ln 5, and I'm going to subtract ln of 2. And here I'll factor out the x. So x I'm multiplying by ln of 2 minus 2 ln 5. And that equals this up here. And now to solve for x, I'm going to divide by this amount right here. So this is going to stay in my numerator. So x equals ln 5 minus ln of 2 over ln of 2 minus 2 ln 5. Okay, this is my exact answer, my solution set, and that approximately would be approximately 0.234. And I think I'm going to keep example 7 for something that we can work on in class. Okay, but other than that, we're just solving equations, and here by doing the log or natural log of each side and then using algebra to solve for x.